You know, you ever wonder if you can breathe new life into an old, tired oil field? Well, it turns out you absolutely can. But, and this is a big but, before you do anything, you have to give it a full medical checkup. Yeah, just like a patient. You've got to know exactly what you're dealing with before you even think about starting the treatment. So, let's dive in.
So, that's our big question today. How in the world did geologists and engineers play doctor to a massive underground rock formation that's miles deep? It's this really fascinating diagnostic process, and it all determines whether an oil field is even a good candidate for a very specific, very high-tech procedure.
And that procedure is all about using CO2. So in our little analogy here, the patient is an aging oil reservoir, and the treatment, well, that's something called CO2 Enhanced Oil Recovery. But you don't just jump in. First, you have to perform a really thorough examination. Okay, so what is CO2 EOR, really? At its core, it's a pretty brilliant idea. You pump CO2 deep underground into an oil reservoir. That CO2 then acts kind of like a solvent. It mixes with the oil that's still trapped down there, makes it thinner and less sticky, and helps push it towards the production wells. It's an incredible way to get oil that we previously just had to leave behind.
And listen, this isn't just a friendly suggestion. It's the absolute golden rule. Every single successful project is built on knowing that reservoir inside and out. If you skip this step, this comprehensive characterization, well, it's like a surgeon trying to operate without an X-ray. It's just a recipe for disaster.
So let's get to the first part of this exam, the initial screening. I want you to think of this just like a doctor taking a patient's vital signs. It's a quick, high-level check to see if this reservoir is even in the ballpark to be a candidate for this whole thing. And it's not a random process at all. It's a very structured evaluation. First, engineers grab every piece of data they can find on the field. Then they run a preliminary analysis against some key benchmarks. And finally, based on all that, they decide if the field looks promising enough to move on to a much deeper look. And these are the vital signs they're checking. Things like, is the reservoir deep enough? Does it have enough pressure to keep that CO2 in a special, liquid-like state where it works best? Is the temperature right? What about the oil itself? Is it the right type to even react well with CO2? And maybe the biggest question of all, is there actually enough oil left down there to make this whole thing worth the effort? All right, so let's say a reservoir passes that initial screening. Now it's time for the physical exam. This is where we start looking at the fundamental physical traits of the rock itself, and it all comes down to two key characteristics, porosity and permeability.
Honestly, this is the best way to think about it. Porosity is like the size of a parking garage. It's the total amount of empty space in the rock that can hold the oil. But that's only half the battle. Permeability, well, that's all about the roads connecting those parking spots. I mean, you could have a giant garage, but if there's no way to drive between the spots, it's totally useless, right?
So the ideal patient, the perfect candidate, has to have both. You need high porosity, so there's tons of oil to recover, and plenty of room to store the CO2, and you absolutely need high permeability so that CO2 can actually move through the rock, get to the oil, and push it out.
Okay, next up in our checkup, it's time for the lab work. This is where we analyze the fluids and the reservoir's structure in way more detail, looking at things you just can't see without some seriously specialized tests. By analyzing a sample of the oil itself, scientists can figure out the exact pressure needed, that's the minimum miscibility pressure, for the CO2 to mix perfectly with the oil. They can also predict how much the oil will swell up, how much thinner it'll get, and just generally how it's going to behave once it meets the CO2. This is all absolutely crucial for designing the injection plan.
And you know, what's in the reservoir is important, but what's above it is arguably even more critical. We're talking about the cap rock. This is a solid, impermeable layer of rock that acts like a natural seal, a giant lid. A huge part of the lab work is making sure this cap is strong enough to hold all that injected CO2 safely underground without any leaks. It is the #1 safety feature.
So after all the screening, the physical exams, and the lab work, it is finally time for the diagnosis. And this is where we often uncover the single biggest potential complication for the entire treatment, something called reservoir heterogeneity. Here's the deal. No oil reservoir is a simple, uniform block of stone. They are incredibly complex, with wild variations in rock properties from one foot to the next. Some spots might have great permeability, while other areas right next to them are nearly solid rock. It's this patchwork nature that we call heterogeneity.
So why does this matter so much? What's the big deal? What happens if you get this diagnosis wrong and just assume the reservoir is way simpler than it really is?
The biggest risk, the thing that keeps engineers up at night, comes down to 3 words: Early CO2 breakthrough. And yeah, it's just as bad as it sounds.
Remember our highway analogy for permeability? Well, heterogeneous means that some of those highways are actually superhighways. If you're not careful, the CO2 you inject will find these super easy pathways and it'll just zip right through the reservoir, completely bypassing the oil you're trying to push out and show up at the production well way too soon. The entire treatment is just wasted.
And that right there brings us to the most important takeaway of all. This whole checkup process, it's not just a simple yes or no test. It's about deeply understanding the unique, complex, messy nature of each individual reservoir, so you can create a custom-tailored injection strategy that actually works with its specific challenges, like those hidden superhighways.
And this really makes you think, doesn't it? The exact same science used to get more oil out is now being adapted for permanent carbon storage. So as we look to the future, it really begs the question, what other kinds of geological health checks are we going to need to perform not just on an oil field, but on a planetary scale to make sure we can safely lock carbon away for good? It's a huge challenge where the stakes couldn't be higher.